We present an incremental layout method for visualizing online dynamic graphs. Online dynamic layouts visualize a series of graphs over time without future knowledge of the time steps. In order to speed up the process of laying out an online dynamic graph, a commonly employed approach is to anchor large portions of the graph and allow only a small subset of the graph to move. Nevertheless, this speedup comes with several trade-offs. One trade-off is when a new node or an edge is introduced. Only that node and its neighbors are allowed to move at that instance. In most cases, nodes are placed near their ideal spot. If two disconnected components merge, the nodes usually cannot reach their ideal spot. Our layout identifies when this occurs by looking at the energy of nodes and allows nodes with high energy to move to their optimal position, known as refinement. Energy levels are mapped from yellow to red, where red represents high energy. Refinement allows only nodes with high energy to move until they reach a low energy state, which is represented in yellow. Let's look at an example of our layout method versus the previous online dynamic layouts. Aging by Gorochowski et al. Is shown on the left and pinning by Frischmann and al. On the right. As the video plays, we can see both aging and pinning having trouble with components merging. Long edges and edge crossings are both present in the two layouts. Our layout, on the other hand, gradually shifts nodes until they reach a better placement. Let's take a look at another comparison of our layout against the two previous works, aging, shown on the left, and pinning, shown on the right. The dataset used is taken from McFarland's study that documents student interaction in a classroom. The dataset does not have the distant component merging, as did the previous example. As the video plays, notice how the node is highlighted by a red ring. In our layout, the node shifts away from the graph, making it easy to read, while in the other two layouts, the node is placed in a location where it is easily mistaken as a connected node. A strong benefit of our refinement technique is that it can be applied to existing layout methods. Here we decide to apply our refinement to the previous work, pinning. Pinning is shown on the left, and pinning with our refinement on the right. Pinning suffers from the same problem as before, long edges and edge crossings. The refinement technique fixes these issues and provides a better spread of the nodes, improving the readability of the graph.